Swayam Prabha. Digital India. Educated India.
Dear students, I welcome you again in the lecture series on mineralogy organized by the Department of Geology and Geophysics, IIT Kharagpur. Today will be the 14th lecture in this program and the 5th lecture on optical mineralogy. In today's lecture, I will continue from where I have left in the last class when I have discussed the interference figures of uniaxial minerals and how the interference figures of uniaxial minerals can be used to determine the optic sign. Today, we will study the interference figures of biaxial minerals, and we will be also using these interference figures to determine the optic sign of biaxial minerals here. Additionally, we will also study properties under plane polarized light. What are they? They will be crystal habit and shape, cleavages and fractures that are present in minerals, the color of the mineral and the concept of pleochroism, and also the relief of a mineral and how the Becker line test can be used to distinguish between minerals of low relief and higher relief. Okay. So, if you remember the biaxial minerals here, if you remember the optical indicatrix of biaxial minerals, so then you must recognize that you in the principal section of indicatrix of biaxial mineral, which is also the optic axial plane, there you have two optic axes here. So, you see here this two optic axis has been shown here, and this optic axis is bisected by a direction which we call it as acute bisectrix, and the angle between these two optic axes we call is the optic axial angle, that is 2V. And in this plane you have a direction which is the bisector of this acute angle and also the bisector of obtuse angle here. So, if you have a situation where you have the direction which bisects the acute angle, then we call it as acute bisectrix, and the one which bisects the obtuse angle here we call it as the obtuse bisectrix. So, what we have here is that depending on among Z and X, which one is the acute bisectrix, that will determine the optic sign of a biaxial mineral here. And this direction here, which is perpendicular to this optic axial plane, we call it as optic normal. This is the Y vibration direction here. And in this particular case, what you have here is that you can have a situation where the acute bisectrix can be vertical, and you can also have a situation where you have optic normal is vertical here. When optic normal is vertical, we can have an interference figure which is called optic normal interference figure, the one that we generally do not use, but for theoretical understanding it is possible to have an interference figure which is optic normal interference figure. But the one that we will be using is this one here, where the acute bisectrix is vertical, and we will be seeing an interference figure which you will be calling acute bisectrix interference figure. And in the skydrawn diagram here, you can have a situation where the acute bisectrix can be vertical. In this case, it is shown as Z, and you have these two optic axes is there, and when Z is the acute bisectrix, the optic sign is, we call it as biaxial positive. When X is the bisector of the acute angle, then it will call it as biaxial negative here. Okay. Let us have a look at this diagram here. This is an acute bisectrix interference figure, and how this can be done if you remember that to study an interference figure, you have to convert the microscope into a conoscopic arrangement here. As we did for uniaxial minerals, what you have to do? You have to use a convergent lens, you have to use a high power objective, and under cross Nichols, you also need to use the Barton lens here. And if your acute bisectrix is vertical, so then the point of emergence of the acute bisectrix will be at the center here. Then you can have an isoger shape something like this, and 0 degree position here. Your vibration directions in the mineral, they are parallel to the polarizer and analyzer vibration directions. So, you will have this kind of isoger here. It will be a black cross, just like an uniaxial interference figure, but there is a difference here. The two arms of the isoger are not symmetrical here. This arm is thin, but this one here is much more broad here. Now, let us try to understand what are the critical points in this isoger. There are two red points that are shown here. These are the points of emergence of the two optic axes here, one here. So, this point of emergence of optic axis is also called the melatoph here. So, one melatoph here and the other melatoph here. And if you can join the two melatophs, that will also pass through BXA position here, and this trace is the trace of the optic axial plane here. And what you also have here is that the perpendicular to the trace of the optic axial plane is the optic normal, which is the y vibration direction here. Immediately you can find out that in this plane, this is broadly parallel to the BXO vibration direction here, or obtuse bisectrix vibration direction here. So, what you can do here is that at any point within this field of view of this interference figure, you can have an idea about the vibration directions of the two rays using a construction called Biot-Fresnel construction. What is that? So, if you are at the position n, which is the point of emergence of the two rays, doubly refracted rays within this field of view, then if you join this point with these two melatophs, then it makes an angle, this angle here. So, the bisector of this angle is this direction. So, one of the rays will vibrate along direction D, and the other ray will vibrate perpendicular to it, which will be this C ray here. Now, if you look carefully here, the direction of vibration of the D vibration direction is broadly parallel to the optic normal vibration direction, that is Y vibration direction here. Whereas, this vibration direction, which is C, is broadly parallel to this direction, which is parallel to the BXO or obtuse bisectrix vibration direction here. Now, if you insert an accessory plate on this figure, you now know that the first vibration direction of the accessory plate is oriented northwest southeast here. So, if you see this, so then in quadrant 1, this first vibration direction of the accessory plate will be parallel to this vibration direction C, which is in most cases will be parallel to the BXO vibration direction. So, after insertion of the accessory plate, if there is an additive effect here, so if you insert the first order red plate or gypsum plate, and if you see blue color in quadrant 1, what you will see in that situation, the blue means second order blue. So, there is an additive effect has taken place here. So, additive effect means the retardation has been added up here. So, that means it is only possible when first vibration direction in the accessory plate has coincided with the first vibration direction in the mineral. That means, this vibration direction will be the first vibration direction here. So, we already know that this ray, that is D, this is parallel to the y vibration direction, or it is the y vibration direction. So, if C is the first vibration direction, that is BXO is the first vibration direction, then which is faster than y? So, if x, y and z are the three vibrations, you know that x is the fastest and z is the slowest, whereas y has an intermediate velocity, then immediately the ray which is faster than y, that is x. So, immediately you know that the BXO will be x. So, acute bisectrix then will be z. So, in that situation the biaxial mineral would have an optic sign which will be biaxial positive optic sign. So, let us move further and see a situation here that you have the first thing here is that how this acute bisectrix interference figure looks like here. The first thing here, if you see this diagram here, in this diagram you see there is a black cross, as we have already discussed here. Only thing, there is a difference here. What is the difference? The shape of the cross or the two arms of the isojet is not identical, and we discussed the thing here. And this we call it as the 0° position here. So, at 0° position, an acute bisectrix interference figure will have a black cross like this. And you all know that this the trace of this optic axial plane in this condition is oriented east to west, and the optic normal in this case is oriented north south. Now, if you rotate 45° from this position, what will happen is that these two arms of the isojet will now split and will become hyperbolic segment here, as this has been shown here. So, there is a curvature you can see here. So, the convex side of the curvature is in this direction, and the other arm of this hyperbola is this, the convex side is this direction. So, this is one of the most diagnostic property of identifying an biaxial mineral using an acute bisectrix interference figure, that is that in 45° position from 0° position, when you rotate to 45° position, what will happen here? The two arms of the isojet will no longer remain straight, but it will split and it will have an curvature here. We call it as the hyperbolic segment. One segment is here and the other segment is here. That is a definite confirmative evidence that this mineral or is part of a biaxial mineral group here. And if you rotate further 45°, now it is 90°, in that situation the optic normal vibration direction will be now oriented east to west, and the trace of the optic axial plane will be north south here. And if you rotate further 45°, so from the initial position, the total rotation of the microscope stage is 135°. What will happen here? Again, the two arms of the isojet will split into hyperbolic segments. Only thing, the trace of the optic axial plane will be now oriented along a direction of northeast southwest, whereas the initial stage, initial 45° position, this was oriented along northwest southeast direction here. And these are some of the examples here, where depending on the 2V value and how the orientation of the acute bisectrix, whether it is completely vertical or it is partially tilted, you can have different shapes of this in acute bisectrix interference figure here, or the acute bisectrix interference figure shows a difference here. But it will be always welcome that if you have an acute bisectrix which is perfectly vertical, so that you have a perfectly centered acute bisectrix interference figure. That kind of interference figure is extremely useful for determination of the optic sign of biaxial mineral, which I will show you in the next slide here. Let us have a look at this particular diagram here. So, this is the one we already told you, this is the 0° position here, and in this 0° position this is the two arms of the isogen. Let us consider two biaxial minerals here. One is weakly birefringent mineral, that means the birefringence value is low, and the other biaxial mineral is a highly birefringent mineral where the birefringence is very high. What will be the distinguishing factor in these two? In case of weakly birefringent mineral, you will not see isochromatic bands or rings, or even if it is there, it will be much smaller in number here. Whereas, in a highly birefringent mineral, you will have these isochromatic bands or rings, which will be symmetrically disposed with respect to these two melatope position here. Now, in case of weakly birefringent mineral, the accessory plate that is preferred is the gypsum plate, whereas for highly birefringent mineral, the accessory plate which is preferred is your quarter lambda plate or mica plate here. Now, let us study this diagram first, that is the weakly birefringent mineral. So, at 45° position, you see that the two arms of the isogen is a hyperbolic segment here, this is the curvature. Now, you see this is the convex side of the isogen, this is also the convex side of the isogen, and this is essentially the concave side here. Now, if you at any point where you have the maximum curvature here, if you draw a tangent, that will be this direction here. So, this direction is the optic normal direction here, this is the direction of y vibration, and this entire trace, this is the trace of the optic axial plane. But importantly, this point here is the point of emergence of the acute bisectrix. So, within this field of view, the convex side or the direction convex to this isogen, this is broadly parallel to the obtuse bisectrix vibration direction, that you can consider this. Whereas, the concave side, this is the direction which is shown by the red, that vibration direction is the projected vibration direction of the acute bisectrix. Very often we call it as BX dash vibration direction, and the one of which I have shown here in the blue, this is the obtuse bisectrix vibration direction. So, within this convex side, you have theoretically two rays here, one is the Y vibration and the other is the obtuse bisectrix vibration. Now, if you insert an accessory plate here, the first order red plate, and if you see in this particular case in the convex side, if you see blue, which is shown here in the blue here, and in the concave side if you see yellow, then what will be the, how we explain this change in interference color here. So, as we know now, when you see blue, that will essentially represent that there is an additive effect has taken place. That means, first vibration direction of the accessory plate has coincided with the first vibration direction, which is oriented along northwest southeast direction, and that direction is your obtuse bisectrix vibration direction. Immediately you can tell that the obtuse bisectrix is faster than the y vibration direction. So, which one will be between x, y, z, which will be faster than y? X will be faster than y. So, x is the obtuse bisectrix. Automatically you can tell that z will be the acute bisectrix. So, this will be a situation of a biaxial positive mineral here, and this is the way I encourage my students to orient the acute bisectrix interference figure in such a way that the trace of the optic axial plane is northwest southeast, and at this condition you just look at how the what is the obtuse bisectrix vibration direction, and that will be oriented northwest southeast, and just you see whether there is an additive effect or subtractive effect on the convex side. In this case you have the additive effect on the convex side and the subtractive effect in the concave side here. That means, I told you in the concave side you have a complementary condition here, that this is the B x dash vibration direction. So, in this region you also have B x dash and also perpendicular to it, that the y vibration direction. That means, if there is subtractive effect, that means fast and slow has coincided. That means, the B x dash we say slower vibration direction. So, which is slower than y? Z is slower than y. So, immediately you can also see the change in interference color in the concave side and tell that this is Z is the acute bisectrix, this is also biaxial positive. So, you can see the color on the convex side of the isoger and also concave side of the isoger to have a confirmative evidence that this is a biaxial positive mineral here. Now, let us have a look at this particular mineral, which is also a biaxial mineral, and this is a highly birefringent biaxial mineral here. So, in 45-degree position, here also you have this particular thing here, that the trace of the optic axial plane is northwest southeast, and this is the direction of Bx vibration direction, and this is your y vibration direction here. Now, in this case you have to insert the mica plate here. So, if you see after insertion what happens, you just see the sense of movement of the isochrones. If you see that the isochrones are moving towards the center, that means that has been shown here. If it moves towards the center, that means in the convex side you have an additive effect here. And what you see in the concave side, you see the development of compensation spot here, as we have seen in uniaxial mineral, when we have seen, we had tried to when we have used uniaxial interference figure, particularly for the calcite mineral, we have seen how the insertion of mica plate, you have compensation spot developed in certain quadrants, and we told you this is a confirmative evidence that the compensation spots are indicative of the subtractive effect here. So, immediately in the concave side, you know the subtractive effect has taken place, that means fast and slow has coincided, B x dash is the slow vibration direction, and you can consider that this is a biaxial positive mineral here, as also you can see there is a rise in the order of interference color here, there is an additive effect. So, Bxo is faster, so Bxo is X, so automatically we know acute bisectrix is Z. So, this is the way or the methodology which you can adapt to determine optic sign of a biaxial mineral, both which is a lowly birefringent or weakly birefringent biaxial mineral or a highly birefringent biaxial mineral, no problem. Okay. So, this is a situation, this is the same situation here. So, there are two minerals that has been shown here. In this case, the one at the top, this is a mineral called aragonite. You know that this is a polymorphic form of CaCO3. This crystallizes in the orthorhombic crystal system, and what is the optic sign here? So, let us have a see that this is birefringence is significantly higher, 0.156, that is why you see you have isochromatic bands or rings here. And the second mineral, this is, you see here that this is muscovite here, and what you see here. So, this is in this case the trace of the optic axial plane is northeast southwest, and then this is the direction that is your optic normal or y vibration direction here. So, after insertion in this case, this example that has been given here, the accessory plate that is used here, this is the first order red plate here. So, in the convex side we see yellow and the concave side we see blue. So, immediately you see on the convex side, if it is yellow, that means there is a subtractive effect has taken place. So, in this case, this is the vibration direction, this is the y vibration direction. So, y is parallel to the first vibration direction of the accessory plate. If there is subtraction, as I told you, we can know that the first and slow has coincided. So, immediately we know y is the slower vibration direction. So, immediately this direction, which is your obtuse bisectrix vibration direction. So, the obtuse bisectrix will be a vibration which has a velocity faster than y. So, immediately we know that the BXO is x and this mineral is biaxial positive. Z is the acute bisectrix here. And in this case, in case of muscovite, you see in the convex side we see here blue, that means additive here. So, y is faster than the BXO. The BXO will be a slower direction, that will be Z. So, acute bisectrix in this case will be x. That is why in that situation this mineral muscovite has an optic sign which is negative here. So, this is the way you can use this your knowledge and you can determine very easily the optic sign of a biaxial mineral. So, up to this stage what we have done, we have studied acute bisectrix interference figure, where the acute bisectrix is completely vertical. Now, let us have a look at another situation here. If instead of acute bisectrix, if optic axis becomes vertical, then what will happen here? When optic axis is completely vertical, then the section that we are dealing with is the circular section of indicatrix of the biaxial mineral here. So, from your knowledge previously, that in such a situation the birefringence will be 0 and the mineral will behave as an isotropic mineral here. So, that kind of optic orientation is very easy to identify under cross polarized light. So, you can among different grains of a biaxial mineral, the grain which is behaving isotropically or under all stages of rotation of the microscope stage, if it is always dark, then that kind of optic orientation you can choose for determining an interference figure, which we call it as optic axis interference figure. And how it looks like? This is the 0 degree position and this is the 45 degree position here. So, what you essentially see here, the optic axis interference figure of a biaxial mineral, you will only see one arm of the isoger, the other arm is here. So, this particular part here and on the other side we do not see this arm here. So, this is this optic axis interference figure is very often called one half of the acute bisectrix interference figure. In 45 degree position, this isoger will be split, will be bent and will show this kind of an hyperbolic segment here, as we have seen previously for an acute bisectrix interference figure. One thing here, within the field of view, you will only see one isoger here, as you have seen here, but the other feature broadly remains the same here. So, optic axis interference figure can be distinguished from acute bisectrix interference figure by having a single isoger in the field of view at a time. Now, let us use this optic axis interference figure to determine optic sign of a biaxial mineral here. So, the same thing here, this is an weakly birefringent mineral and this is a highly birefringent mineral. We distinguish between these two by knowing this distribution of the isochromes or isochromatic bands here, which is present here and which is absent here. Now, other things remains the same. This is the convex side of the isoger and this is the concave side of the isoger. the trace of the optic axial plane is northwest southeast, and the BXA is somewhere, position is here, but the convex side we already know this is broadly parallel to the BXO vibration direction, and this particular tangent to this isoger here, this is parallel to the optic normal vibration direction or Y vibration direction here. So, after insertion of the first order red plate, if you see blue, so immediately you see this is an additive effect here, first and first has coincided. That means, the BXO direction is the first vibration. So, BXO is faster than Y. So, BXO will be X vibration, automatically Z is the acute bisectrix, and also you have seen on the concave side here you have a fall, that is subtractive effect, because this is the first order yellow here, and from there directly you know that BXA dash is a slower vibration direction, that will be Z. So, your acute bisectrix is Z here, and you can also orient it where the trace of the optic axial plane, instead of northwest southeast, you can make it northeast southwest, and you can use your knowledge and can determine the optic sign here. And this is the same thing that has been followed here, and if you see here that if you have in the convex side, if there is a convergence of these isochromatic bands towards the convex side or the center, that means you have an additive effect here, and if you have a compensation spot in the concave side of the isoger, so there is a subtractive effect has taken place and the isogers are moving away from the center. That means, your BXA dash is a slower vibration direction, that is Z. So, this is a biaxial positive mineral here. So, using both acute bisectrix interference figure and optic axis interference figure, it will be possible for you to determine optic sign of a biaxial mineral. Now, let us see the utility of optic axis interference figure. The other utility of optic axis interference figure other than that of determination of optic sign is to have an approximate idea about the 2V or optic axial angle. So, you see a situation here, the shape of the isoger, if it is like this, so then the 2V is 0. So, it looks like an uniaxial mineral here, and if you see the curvature of the isoger in the 45-degree position, if you see progressively becomes less and less, then 2V becomes progressively increased. So, when you have completely straight or planar, 2V is equal to 90 degree, and in that situation we call a biaxial mineral is optically neutral, and we cannot determine optic sign for that kind of mineral. So, this is an example how the depending on the curvature you can relate it the 2V value here. You can see from 0, which is uniaxial, and progressively as the 2V increases, how the shape of the curvature of this isoger in 45-degree position in an optic axis interference figure, that gives you an approximate idea about the 2V of this mineral. And you will see when you will be studying on your own, you will see different biaxial minerals have different 2V, and this is very nicely shown here. Now, if you see here that in this particular case, if you see this particular mineral here, that is sillimanite, here the 2V is very low, 25 degree, and that is why you have a very large curvature. Although this is an acute bisectrix interference figure here, we can see the curvature here. Now, in this case in ulastanite, the 2V is moderate between 36 and 42 degree. So, here you have an intermediate curvature here, and in case of clinopyroxene, if you see here the 2V has increased to 60 degree, immediately you see here the curvature has decreased. So, it has become more straighter, and for phosphorite crystal where 2V value is 90 degree, it is very straight here. So, this is in natural minerals how we can see how the 2V values gives you an idea, a 2V value can be inferred from the shape of this isoger here. Okay. Let us have a situation here. This is a test case. Very often I ask my students that how it will be possible for you to distinguish between an isotropic, uniaxial and biaxial mineral. So, let us consider that under cross Nichols there are 3 minerals A, B and C. All these minerals are dark, that means they are all under extinction positions. Immediately you can tell that all the 3 minerals represent circular section of their indicatrix. Now, how do you know then which one of these is isotropic, which one is uniaxial and which one is biaxial? So, what it will happen here is that if these are the circular section of the indicatrix, so essentially you will be seeing the optic axis interference figure for uniaxial mineral and for biaxial mineral. So, if you arrange a conoscopic arrangement here, so what will happen? For isotropic mineral you will not see any interference figure, but for uniaxial mineral you will have a perfectly centered optic axis interference figure, and in that situation the isogers will remain stationary and will not move from its position during rotation of the microscope stretch. So, that will be a definitive indicator that this is an uniaxial mineral. Whereas, in case of biaxial mineral, the optic axis interference figure you now know you will only have one isoger, and in 45-degree position you will have this kind of hyperbolic segment will be developed here. So, using this shape of this isoger you will be able to distinguish that this is a biaxial mineral here. So, mineral C is biaxial, mineral B is uniaxial and mineral A is an isotropic mineral here. Okay. So, let us now come to the optical properties that we study under plane polarized light. So, generally what we study? We study crystal habit, the shape, cleavages and fractures, as well as other properties which we will study slowly here. So, what is important here? You see what is habit here. You see certain minerals are equant, particularly minerals belonging to isometric crystal system. They are in all the 3 dimension broadly the same distance here. So, these are some minerals, if you cut they will show like this, they will show as equant minerals here, for example garnet, and there will be other minerals which are tabular shaped here. So, in tabular shaped minerals, so these are just like tablets. So, if you have a section this one perpendicular to the C crystallographic axis, you will have this kind of broadly square shaped shape of the crystal. Whereas, if you see a section which is this section here, this will be slightly elongated shape you will be able to see. And in case of biotite, if there are a basal cleavage here, you will see this biotite as flaky minerals here. And in some minerals, for example, in pyroxene and particularly amphiboles, it grows along the C dimension much more preferably than in other dimensions. So, they are elongated and prismatic habit is there. And crystals, some of these crystals we also see very well developed crystal faces here. So, when you have very well developed crystal faces, so I have given some examples here. So, this is zircon crystal, this is sanidine crystal, this is clinopyroxene here, this is garnet and this is lucite crystal here. These are all well developed crystal faces here. Now, what happens here when these well developed crystal faces are in magmatic rocks or igneous rocks, we call the term or use the term euhedral. But in metamorphic rocks, where garnet is a very common mineral, the well developed crystal faces if we have, we call it as idioblastic. So, what I would like to emphasize here, certain minerals have very well developed crystal faces, and you also have partially some faces are well developed, some are not well developed. We call it as anhedral shape, and if all the faces are poorly developed, we call it as anhedral shape, and when you have some of the faces are well developed, others are poorly developed, we call it subhedral shape here. Now, let us also see how the habit of a particular crystal depends on its optic orientation. I give an example with a mineral called titaniferous augite called titan augite here. So, this is the 3-dimensional shape here. Now, if you have a section perpendicular to C, which is called the basal section or parallel to 001, this augite will have 8 faces here. So, there will be 8 faces here. So, this is like this, and you have 2 sets of cleavages that will be at 90 degree here, as is shown here. Whereas, if you have a section which is this section here, let us say for example, parallel to 010 section here, parallel to 010 face, you will have a prismatic face like this. Whereas, if you have a section parallel to 100, so you have prism faces, but also you have these 2 faces which will meet at a point here, and both on the top and on the bottom. So, how a particular crystal habit will be there is also dependent on its optic orientation here. Okay. Now, let us have a look here that certain minerals can be distinguished on the basis of their cleavages. Pyroxene group of minerals, particularly in basal section, have this kind of cleavages, 2 sets of cleavages. These are prismatic cleavages, and the angle is broadly 90 degree. So, by just seeing this angular orientation of 2 sets of cleavages, you can infer on the basis of other evidence as well that this is a pyroxene group of mineral. Amphibole group of minerals, on the other hand, also have 2 sets of cleavages in basal section or parallel to 001, but this angle is around 56 degree, or you can say and approximate it as 60 degree, which is a characteristic of the amphibole mineral group here. In biotite, you have 1 set of basal cleavage here, and these are, it produces a flaky habit here. In say for in kyanite, you have 1 set of perfect cleavage, and at a high angle to it, you have another set of direction which we call it as parting here, and that is a very characteristic of kyanite. In sillimanite, also perpendicular to the basal section, you have cleavages parallel to the diagonal here, and that is also characteristic of, say for example, in this particular sillimanite crystal here. In andalusite, you have 2 sets of cleavages here, very close to orthogonal direction here. And there are also other minerals here which do not have cleavage, but they have irregular fractures here, as we see in garnet or in olivine crystals here. And this is the one which you also see in garnet, but this is a very important aspect here. This was a quartzite crystal originally, which ultimately converted into quartz. This is a very high pressure polymorph of silica here, and because of transformation of this eclogite from its relatively deeper level or transport to the shallower level, there is a volume expansion, and there are fractures, radial fractures from this quartzite has taken place in garnet here. So, you have certain minerals which have fractures which lack cleavages. There are minerals which have well developed cleavages here. The other important property under plane polarized light is color of the mineral, and we call and also a pleochroism. So, minerals color is a function of the degree of transmission of white light through the mineral. So, in general, crystals absorb some wavelengths and transmit others. So, this is shown with this diagram here. So, you see the different wavelengths of the white light. So, you see red, orange and yellow. This component of wavelengths are preferentially absorbed in certain cases, and you see violet is also absorbed, and green and blue are allowed to transmit. So, immediately you see the color will be different. So, if none is transmitted, so if when all wavelengths of white light are transmitted, the color of the mineral will be white. If none is transmitted, it will be black. If some of the wavelengths are absorbed, the mineral color will be different and we have different hues here. So, this is important here. And isotropic minerals, the light absorption will be equal in all directions. you will see a single color in all optic orientation here, because you know that this is the circular section of the indicatrix. So, you will have only one vibration here. For anisotropic minerals, light absorption may be heterogeneous, and for different vibration there will be different absorption, and there will be a change in color with optic orientation, and this we call it as pleochroism or dichroism here. So, I give you an example of color of a mineral of isotropic mineral group which crystallizes under isometric crystal system. These first three, they are different spinels of different composition. These are green spinel, these are colorless spinels here, and these are brown spinels here. So, whatever you rotate in whatever direction, the color will not change. And this is a garnet crystal here, which is also pale pink, and you can also say colorless, and this is a sodalite, where you see slightly bluish color here. This is also an isotropic mineral here, and this is Hawin group of sodalite here. So, this isotropic mineral group, their color, they will remain the same under different optic orientation here. Now, let us now define this term pleochroism and dichroism. So, these two terms I will differentiate shortly, but both of these indicate a property of the mineral of differential absorption of light waves at different optic orientations, leading to a change in color of the mineral under plane polarized light as the microscope stage is rotated. Dichroism is a characteristic property of uniaxial minerals. There are only two absorption colors corresponding to extraordinary ray and ordinary ray. So, immediately in the principal section of the indicatrix, where you have E vibration direction and O vibration direction, you can have two colors corresponding to O ray, we call it O color, and you can have a color corresponding to E vibration direction or parallel to the optic axis, we call it as the E color here. But if you see the circular section of the indicatrix, you will have only color corresponding to the O vibration direction. And the best example of a dichroic mineral is tourmaline. Pleochroism is the property of in a biaxial mineral. Theoretically, you can have three colors here corresponding to X, Y and Z vibration direction. So, you can see X and Z colors in the principal section of the indicatrix, Y color in the circular section of the indicatrix, or in basal section, that is parallel to 001 optic orientation, where you can have Y associated with either X or Z. The examples of this pleochroic mineral are amphibole, orthopyrox and biotite, and I can show you a large other minerals which are pleochroic here. So, this is, you see, this is piemontite, this is manganese epitode. You see the color of this mineral in different optic orientation in shades of pink. This is glaucophene, the color in shades of blue. The different minerals, different optic orientation of the same mineral is showing under plane polarized different colors. That means, under different vibration direction or different optic orientation, there are differential absorption of wavelengths of white light. This is sapphirine and this is viridine, this is thiolite, and you see this is chloritoid and this is biotite. You see there are two varieties of biotite. Here the change in color is from pale yellow to dark brown, and here biotite, particularly when its composition becomes titanium rich, here the color, pleochroic color has changed. This is orange to brown, yellowish brown it has become. And you have also azurinogeite and also epidote with high concentration of ferric, that means with high pistacite content, your epidote is strongly pleochroic here. Okay. Let us try to have an understanding how the different colors can be identified here. Let us consider the mineral tourmaline here. So, if you have an optic orientation perpendicular to the C crystallographic axis, in this case this will be the circular section of the indicatrix, and you have a color which is dark brown here, and this will be essentially color corresponding to the y vibration direction. But if you have an optic orientation which contains the optic axis, that is C parallel section here, where you will have both E vibration and also O vibration direction here. When the O vibration direction is oriented parallel to the polarizer vibration direction, you have a color which is brownish. When it is rotated 90 degree, so that the E vibration direction becomes parallel to the polarizer vibration direction, then this color is colorless or pale colored here. So, then you can tell that a pleochroic formula of tourmaline, where E is equal to colorless, where O is equal to brownish yellow here. Now, let us come to the pleochroic minerals in the orthorhombic. So, pleochroic colors have to be seen in minerals belonging to the orthorhombic, monoclinic and triclinic system. So, I first start with an actinolite mineral here. So, here in the basal section here, you can have a situation where when this is parallel to x, so x vibration direction is oriented parallel to the polarizer vibration direction, you have a pale yellow or green color. And when you rotate 90 degree, in this you have the y vibration direction, that will be your y color, that is green. But if you have the principal section of the indicatrix or xz section, then when you orient z vibration direction parallel to the polarizer vibration direction, then the color is bluish green. So, accordingly you can determine, depending on the different optic orientation of actinolite crystal, the color corresponding to x, color corresponding to y and color corresponding to z. Similarly, you can also develop or find out the color corresponding to another amphibole, which is sodic amphibole glaucophene. So, in the basal section, where you have two vibrations, one parallel to x, you have light yellow, and if you rotate 90 degrees, so that you bring y vibration direction parallel to the polarizer vibration direction, then the color of the mineral is lavender blue. Now, if you see the 010 optic orientation, which is the principal section of the indicatrix, then if you orient the z vibration direction parallel to the polarizer vibration direction, the color of the mineral is deep blue or called ultramarine. So, in this way you can calculate the color corresponding to x, y and z. So, this is the pleochroic formula of glaucophene here. The other important property of that is to be studied under plane polarized light is called mineral relief. What is the definition? The degree to which a mineral grain or grains appear to stand out from the mounting medium, whether it is an immersion oil, Canada balsam or any other mineral, we call it relief. This is also an indirect measure of the relative refractive index, del n, between the mineral and the epoxy or the cementing agent here. And the relief, we can arrange the mineral according to relief, low relief mineral, moderate relief mineral, high relief or very high. So, if you say that 1.54 is a reference relief, so the minerals whose relief is higher than that of 1.54. So, for example, zircon, which is 1.95 is very high. So, you see relief, this mineral looks to be stand out from the surrounding minerals like quartz here. This is garnet, which relief of 1.8 is also looks like that is a very high relief, it stands out here. And this is a mineral which is a relief of 1.7. This is muscovite 1.6. You see progressively this standout feature progressively decrease, and when it is albite, which is very close to that of quartz, so the outline is gone. And there are minerals which has very low relief here. We call it as negative relief for those minerals. The example here, potash feldspar and fluoride. Now, in this particular situation, so particularly for minerals whose relief is very close to each other, we generally use a technique called Becquerel method to distinguish between minerals whose relief is low and very close to each other. Now, what is a Becquerel line? You see, Becquerel line is a band or ream of light visible along the grain boundary in plane polarized light when the grain mount is slightly out of focus. So, like this. So, this white light is the bakelite here, and this is a crystal orthoclase whose refractive index is 1.51 to 1.52, and the mounting medium, this is 1.54 here. So, this bakelite is to be studied in medium or high power objective, and where you will close the aperture diaphragm. So, that you minimize the entry of light in the mineral. Now, what you have to do here? So, how your bakelite test you can employ here? So, in this case what you use here is that you have a situation, let us consider two minerals are side by side, the mineral 1 and mineral 2. The mineral 1 has a lower relief, whereas the mineral 2 has a higher relief, and their boundary is slightly oblique here. And when you are seeing this, the plane of focusing is this. Now, we can do two things here. One is that you can lower the stage. So, if this is the microscope stage here, this is the objective lens here, and this is the position of mineral here. So, if you lower the stage, that means you raise the distance between the objective lens and this particular mineral. So, something like this. So, you increase the distance, then what will happen here? This white line, which is the bakelite, is moves towards the mineral of higher refractive index, and the converse will be when this objective stage is raised. That means, in that situation distance will decrease here. So, when distance decreases here, so the bakelite moves towards the mineral of lower refractive index. So, this is essentially we call it as the bakelite test here, and this is shown by a picture here, where quartz is surrounded by a glass. Glass has a refractive index of 1.53 and quartz has a refractive index of 1.55. So, when distance is lowered here, or what happens here is that you see that the bakelite moves away from quartz and moves towards the glass here. That means, when the distance is decreased here, so the bakelite will move towards a mineral of lower refractive index. So, this is where you have the perfect focus is here, and when you have increased the distance here, so you see that the bakelite has moved towards quartz, that is quartz has higher relief. So, it moves towards higher relief here. So, what is the thing here? So, when the stage is lowered, we are increasing the distance between the objective and the sample, and the bakelite moves into the mineral of higher relief. So, this is this test that we undertake to distinguish between two minerals which have lower relief and is very close to each other, and this we generally employ to distinguish between potash feldspar and quartz. So, my students, sometimes my students they try to identify potash feldspar on the basis of twinning. So, particularly when potash feldspar is in a igneous rock here, so where the twinning is very well developed, particularly in microcline you have cross-hatch twinning, or you have orthoclase or sanidine where you have Carlsbad twinning, it is very easy to identify this is a potash feldspar. But in metamorphic potash feldspar, very often twinning is lacking here. So, in this kind of untwinned potash feldspar, you can employ bakelite test to distinguish between quartz and potash feldspar without doing any other thing. Quartz has higher relief than potash feldspar. Okay, with this I come to an end to this optical mineralogy course, and in this process I also come to an end to the topic that I have covered in the 14 lectures that I have given to you. So, where I have covered the crystallography component, and also I have covered the optical mineralogy component here. I hope that this particular teaching will be useful to you, and you will be able to understand what has been taught here. Thank you once again for your patient listening.